Okay, so welcome to a tutorial on observational studies. Just to warn you, this will be a tiny fraction of what you possibly learn about observational studies. We only have 90 minutes. It's a very exciting topic. I'm sure you're all ready for your lunchtime nap, but I promise that this is riveting enough to keep you engaged. So I'll start with a motivating example, and we'll go through the necessary evil of comparing observational studies to randomized experiments, right? Because as testers, that's usually what we're kind of focused on. We're focused on experimentation. Well, what if you couldn't, right? So we'll ask the question of what happens, what do we lose, how we can possibly make up for it. So we'll talk about some adjustment strategies. I will sort of confess in the beginning that I'm biased as far as adjustment strategies. There are different philosophies in observational studies, and I was, as a student, kind of brought up with one, and that's the one I believe is the best. We'll talk about that one, and we'll also talk about some others, and I'll give you some references as well where you can read about more. But you'll see a lot of references through this talk. I don't think you'll walk away experts in observational studies, but you'll know what kind of questions to ask, you'll know what to watch out for, and you'll know what to read and what to ask about, what to Google after this. So as a motivating example, I'll give a study that I actually did at my first job when I worked at the Center for Naval Analysis. And I worked on a team that worked with Navy personnel data. And the interesting thing about our military is that it's a closed personnel system, right? So once somebody gets in, if you lose them, it's over. And it's especially important to retain the good folks, and sometimes it's important to get rid of the not so good folks. And so in the Navy, that's a really big issue. It's a very technical organization. They invest a lot in their sailors and officers, a lot of training. And so they worry about retention a lot, because once you lose a person, they're gone. And if you're trying to build a certain pyramid of ranks, then that's something you really have to watch out for. So the Navy cares a lot about retaining its officers, especially the right kind of officers. And an officer, once they've worked long enough in their community, once they've had a certain job, they can apply for lateral transfer to another community. They can learn a new skill, and they can leave their current community. And that's called a lateral transfer. And usually, you have to fulfill your initial obligation to the Navy before you do that. Usually it will be an unrestricted line officer, on average, right? A warfighting officer, like a surface warfare officer, applying for a restricted line position, so maybe applying to be in public affairs or something like that. And from the Navy's perspective, that's a good thing. If the officer now knows, has learned a bunch of skills, they can now stay in the Navy and serve longer. Well, there's a process for lateral transfers. An officer has to fill out an application. This happens twice a year. And then a board convenes. And the board decides whether the officer makes it into that other community, right? And some factors that go into that decision are, first of all, is there enough of a need for that person? That's usually published ahead of time. People only apply for jobs that they know are available. But there's some other decisions that go into it. First of all, the board decides if the officer is best and fully qualified. And that's Navy wording. Best and fully qualified compared to other applicants, right? So they obviously just want the best person for the job. That makes sense. But there's a trick there. If the officer gets approved, at that point, his supplying community, and I say his because it's primarily men, so I'm just going to proceed with that for the rest of the talk, but his supplying community has to let him go, right? And if the officer is needed in his supplying community, his community manager might decide that this is not going to work. So the officer then has to stay. Now, the problem is that some officers, after they get denied, they leave at higher rates than officers who get approved, right? And so the question that we got was, should these supplying community quotas, that's a very controversial kind of thing to do, right? Somebody applied for a job, they clearly want out, and you don't let them go. If they end up leaving the Navy anyway, well, then you just lost an officer that you didn't need to lose, right? So you lost him from your community anyway, and if this was a good person, you could have at least kept him for the Navy. But it's not that simple. The reason for denial is not in the data. We don't know if the officer got denied because that officer just wasn't best and fully qualified, because that officer maybe just wasn't eligible for transfer for some reason, or because his supplying community didn't let them go. We don't know that. And so the question that we were asked as researchers was, should the supplying community quotas be reconsidered? So in other words, what we care about, is, do these denials cause people to leave? So if somebody applies and you deny them the opportunity to transfer, which they could have had otherwise, is that person lost anyway? Or could you have kept that person? So we're obviously, we care at that point about the causal effect that denial has on the officer's retention, right? Well, again, the problem is that officers get denied for different reasons, and none of those reasons are random, right? Those reasons are either because they're not best and fully qualified, which you could almost maybe consider random in the sense that you don't control who else applied for that position. But certainly if the officer is just not that good, that's a red flag, right? And the problem is exactly that if the officer just wasn't that great at his or her job anyway, that person is likely to leave the Navy anyway, because chances are they already know that they're not that great at their job. Maybe they got passed for promotion, for instance, and they were possibly on their way out already. So that's the problem, is that the officers who get denied are probably not at all like the officers who got approved. And so then when we talk about the causal effect of this denial process on their retention, it's very hard to know which officers to compare to each other officers. How do you figure out the right subset of applied and denied officers to where you can talk about the causal effect? Does that make sense? So there's a third lurking variable here, failure to promote, for instance, or officer quality, right, which we can measure by their failure to promote, which possibly could be causing both things, denial and also leaving the Navy. So the big question was, how do we compare retention among these officers? And wouldn't it be nice if they got approved and denied at random? Well, certainly for me as a researcher it would be, probably not for the Navy. And if you talk to some of these officers, they might say that people get denied and approved at random. But in our case, we have enough data to see that that's not true. And in fact, approved officers are different from those who get denied. And those reasons for denial might also be the reasons they leave the Navy. So how do we adjust for this lurking variable, for these confounders, right? If we didn't randomly assign people to get approved and denied. And even more importantly, what do we do with variables that we didn't observe, that we didn't know to measure, that are not in our data? And can we ever possibly estimate a causal effect of this policy on officer retention? So that was our motivating example. Now we'll move into a little bit of theory, I guess. In a randomized experiment, the treatment is usually randomly assigned, right? And a lot of this research, I'll go through some of the history, but it's medically based, and so you see a lot of treatment and control kind of wording. But usually these techniques, you'll see them come up in the medical literature, and you see them come up in public policy. And so here, again, treatment is not randomly assigned, but if it were, then the probability of treatment is the same for everyone, right? It doesn't have to be a half, but it's the same for everyone in the sample. Or at least if you do a block randomized experiment, it's the same for everyone in that block. So everybody's similar to each other on average. If you run a big enough experiment, you might expect that the control group is similar to the treated group. On average, they should look the same. And importantly, they'll look the same on variables you measured and also on variables you didn't measure. And by the way, that only happens for big experiments. So when we run small experiments, you almost never actually see this. And then if your groups are just about the same on all important variables, then you might expect that whatever difference in outcome you observe is due to treatment alone, because nothing else was different. In an observational study like this one, treatment assignment is not random at all. Some people are much more likely to receive treatment, be denied in our case, than others. And the big flaw with that, from a research perspective, is that your treated group might end up not at all the same as your control group. So in our case, we suspect that that might be the case with officer quality. We suspect that our denied group is probably worse quality than the group that was approved. And so you might end up with groups that look slightly different, not just on observed variables, but also on unobserved variables. And then if you observe a difference in outcome, how do you attribute that to treatment alone? So taking you through history a little bit. So from Fisher, 1930s, right, we know about randomized experiments. Observational studies took a lot longer to develop, and really their development started coming around in the 1950s and 60s when people took a great interest in the relationship between smoking and lung cancer. That really was the motivating application there. And so in 1960s, that's when the field was really established with the help of Cochrane, who clarified the benefits of observational studies. If you properly plan them, if you properly execute them, and properly analyze them, you can actually draw a lot of inference from them. And that certainly came true for smoking and lung cancer. Right now, we're all comfortable with that association. An experiment was never conducted to kind of estimate these causal effects. And in fact, for a while, people thought that it was coffee that was connected with lung cancer because smokers tend to also drink a lot of coffee. So we laugh at that now, but that was a serious thing that people worried about. But in the 1960s, with the help of a lot of observational data, that association, that causal association, was finally established. And that really motivated a lot of researchers to start thinking about observational data. And so the two characteristics that Cochrane specifies were if your objective is to elucidate cause and effect relationships, and if it's not feasible to use controlled experimentation, right? So usually it's not feasible to use controlled experimentation because of cost or because of ethics. Those are kind of the two main reasons for observational studies. There are all kinds of observational studies, and their definitions aren't exactly mutually exclusive either. But you can look at cross-sectional studies, so you collect individual level data at a specific point and just look at that. You can talk about case control studies. This is when you already have individuals who have experienced a condition, say lung cancer or leaving the Navy or not, and you sort of look at their history backwards and try to figure out how many of them were exposed or not exposed to a certain treatment. There's cohort studies. That's what we're doing here, right? When you start observing exposed and unexposed people and sort of subjects and track them over time and see what kind of responses they develop. And then there's ecological studies where you look at the entire population and try to correlate something like disease prevalence with amount of vitamin D they receive from sun or something like that. And so following Cochrane's sort of foray into observational studies in the 60s, in the 70s, we saw the development of philosophy called potential outcomes. And that's where you'll see a lot of observational studies theory is based on now, is this concept of potential outcomes. So it looks a little mathy, but really just consider each officer that could be exposed to treatment, denial, or it could be in the control group if they get approved. That officer has two potential reactions to each treatment, right? That officer can leave the Navy or stay in the Navy. So in the first case, this is RT, this is the officer's response to treatment. So this person was going to have an outcome of 0, both if he were denied lateral transfer or if he were approved for lateral transfer. So his difference, this is the treatment effect, right? The difference between your treated and control outcome is your treatment effect. So for that officer is going to stay in the Navy no matter what. And so for him, the treatment makes no difference whatsoever. Getting denied makes no difference. This person, oddly, chooses to stay in the Navy if denied, and the approval causes him to leave. That's very irrational, and we don't actually expect this to ever happen unless something else came up for that particular person. This is the person that we're most worried about. This officer would stay in the Navy, so have a leaving outcome of 0 if they were approved, and they would leave the Navy if they got denied. So if we wanted to change the supply and community quota policy, this is the person that we could potentially keep by not denying them the opportunity to transfer. And then this person is planning to leave the Navy no matter what. Maybe they apply for a lateral transfer out of interest or something, maybe just in case, but they're probably going to go anyway. Does that make sense? Okay. So in other words, each person, each officer, has two potential outcomes. Their reaction to treatment and their reaction to control. Their retention decision if they get denied, and their retention decision if they get approved. And the difference between them is the treatment effect. And the problem, it's called the fundamental problem of causal inference, is that for each person, you only observe one of those. You never get to observe both, right? So if we go back, for all the subjects that received treatment, for all the officers that were denied, we're observing this column. And for all the officers that were approved, we're observing this column. Since nobody gets both, we never get to observe both. And so, our treatment effect is just the difference between the potential outcomes. And the average effect of the treatment is exactly what it sounds like. It's the average of those guys for all the officers in our sample. Well, it looks like an arithmetic problem here. It's no longer an arithmetic problem if you never actually observe this quantity, because you only ever get one of those, right? And the other one's called a counterfactual. So, and by the way, this average treatment effect, that's not the only thing you can estimate. So especially in the policy world, we also estimate things like attributable effects. So that's how many officers specifically left the Navy just because they were denied. And also there's something called average effective treatment on the treated. And so you worry about that sometimes in medical literature and sometimes in policy literature. There are some people that are just never going to be selected into treatment. So when I was in graduate school, I consulted on No Child Left Behind. And it's an amount of funding and training that goes to schools that are not performing well, right? And so that's very much a non-randomly applied policy. Well, schools that are performing well will never be part of it. So it makes no sense to estimate an average treatment effect or the effect of No Child Left Behind for all schools. It'll never be applied to them. It'll only be applied to schools that look a certain way. And so if you have a policy that will only be applied to subjects that look a certain way, you might consider what is the effect of that treatment only on those subjects and not on the entire population of subjects. But nevertheless, this is the most common thing that you might want to estimate. And again, the problem is that you can't really compute this quantity because for each officer, you only ever get to see this or that and never both. So what kind of questions would we have asked if the Navy did this at random? Well, we would ask, what's the causal effect of denial, right? Does denial cause officers to leave the Navy? And that's a Fisherian kind of question, just is there an effect, right? And you could do this test, especially if you had a proper randomized experiment. You wouldn't even have to necessarily worry about any other covariates. You could just do a Fisher test, just say, yes, there is an effect, or no, there is no effect. If you cared about how much of an effect there is, you could run a regression or do some other kind of analysis to estimate how much the probability of an officer leaving goes up just because they got denied. But we're not so lucky, right? We don't have a randomized experiment. And so we start asking different questions, right? Our questions are, what would the officer have done, right? So we're back to this, and for each officer, we only have one of these. We're going to try to think of the other component, whatever is missing for each person, the counterfactual. That's what we're interested in. And that's the potential outcomes framework. We also, because this is an observational study, we no longer expect that our important variables, that our covariates are balanced between the two groups. We expect the quality of officers to differ. We might expect demographics to differ. We expect all kinds of things to be different between those two. So now we have to worry a lot more about adjusting for covariates, at least that we observe. That's probably the best that we're going to be able to do. And we can still conduct tests of no effect once we've properly adjusted for them or once we think we've properly adjusted for them and estimate the magnitude of the effect of denial. But there's always kind of that damper on things. And then the worst question of all is, what if we miss something important, right? What if there's hidden bias? What if there's a lurking variable out there that can just upset everything that we found? So that's kind of the line of thinking here. It's a lot more, it's a lot easier to argue with this than it is to argue with that. And I'll mention that that's an important part of it that we have to worry about in observational studies. You have to be able to tell a plausible story, right? If there's no story, then you become a lot less persuasive. This has to usually concur with some kind of other theory that you might have about how things actually work. So I'll go through some adjustment strategies. And this, as I warned you at the beginning, I'm a little bit biased. I kind of grew up on this, on matching and stratification and propensity scores. That's one school of thoughts. It's pretty popular specifically with statisticians. There are a couple of other really popular approaches, difference, indifference, and instrumental variables. Those tend to be popular with social scientists, I've noticed, with political scientists and with economists. And then there are actually other schools of thought, especially for computer scientists. And you can read more about those. Like, I recommend a book here by Jadair Pearl. But we'll go through these potential adjustment strategies. Before we get into those, there are some standard assumptions that we have to make to proceed. And I don't feel badly about those because we make assumptions in everything we do as statisticians. So the first one is SUTVA, the stable unit treatment value assumption. And that has to do with each person's outcome has to be independent of everybody else's treatment assignment. So if I'm an officer and I'm deciding whether or not I want to leave the Navy, that has to be independent on whether Stephanie got denied or approved for lateral transfer. That assumption is always made, and it's almost never tested. And an important point is that when you're doing this with human subjects, they actually can interact with each other. And so that might be violated when subjects interact with each other. If Stephanie is my best friend in the Navy and I think she's been unfairly denied an opportunity for lateral transfer, I might leave the Navy as in sign of protest, or at least my probability might go up of doing something like that. So again, this is usually assumed, and in many cases, there's no reason to doubt it. But when you have interaction between subjects, that's something to worry about. And there's no good way to test it, for the record. Does this make sense? Okay. Another one, strong ignorability of treatment assignment, or the conditional independence assumption. That one is pretty simple. It just states that there's no lurking variable. That whatever we have in our brand data set, whatever we know about these officers, that's what matters for their decision to leave the Navy or to stay. And you can actually test sensitivity to this assumption, so I'm not too worried about this one. It's a strong assumption and it's scary, but you can also test how your answer changes if this is false, though most people don't. But again, so conditional independence assumption just means that your approval or denial depends only on things we measured and recorded and doesn't depend on something that we've never thought of, like coffee. And then finally, common support condition. So in statistics language, common support condition means the probability of assignment to treatment is bounded away from 0 and 1. In English, it means that each officer has to be able to be approved and denied. There's nobody there who for certain will get approved. There's nobody there who for certain will get denied. And that there's hopefully a decent amount of overlap in distributions of probabilities of those officers. So in other words, it just tells you these officers are comparable. You might have to work kind of hard to figure out whom to compare to whom, but this says that they're not completely different populations. You should be able to compare them. Does that make sense? Okay. So now that we've assumed the world, so the curse of dimensionality, I know that we're probably familiar with it in the way that it comes into randomized experiments, right? When you're just trying to plan an experiment around too many factors. It's not entirely different here. There's a lot of variables that matter to officer approval and denial, and how should you adjust for them? If you had a randomized experiment, you might not need to adjust at all, right? But you are in an observational study situation, you have to adjust for them because chances are they're not balanced. And then the next question is how you might go about this. So one, there might be too many to just throw them into a regression. In this case, it was too many. But also, if you are going to, and I'm kind of moving ahead a little bit, if you're going to match people up, match treated and control subjects, how do you figure out when they're close enough? On what variable, if you have 20, right? And so if you have 20 covariates with just 2 level each, that's over 1 million different cells that you could match people on. How do you decide which ones are more important to balance? And so there's been a lot of focus. We're now moving from the 70s to the 80s on reducing the dimension of the covariate. Because, again, if you try to match somehow or regress on all of these, it probably won't work. And the problem is you can't match exactly, right? Because there's just too many. And nobody knows what approximately means. What does it mean to match, exactly on gender? Maybe you can figure that out, but also approximately on age? What does that mean exactly? And it becomes this just intractable problem, and whatever you do, somebody will find something wrong with it. So it's better to just not do that. And instead, in the 80s, there have been a huge advancement in observational studies is the invention of propensity score. And then very recently, something is called a prognostic score. It's a much more controversial quantity. It doesn't sound like statistics should be a controversial kind of science, but there are fistfights. I kid you not. So the propensity score, something that came around in the 1980s, in 1983 specifically. It's a really big paper by Rosenbaum and Rubin. And the basic gist of it is that, so in an experiment, what would you do? In an experiment, you'd compare subjects that have the same probability of being exposed to treatment, right? So you would, in an experiment, you'd find an officer who is this much likely to get denied, but got actually approved, and this one who is just as likely to be denied and got denied, and you'd compare them, right? That would be a block in a randomized experiment, that pair. So you're trying to look for subjects that have the same probability of being treated, of being denied. That's what an experiment would look like, or a block randomized experiment. And so what we're going to try to do using the propensity score is we're going to try to recover that experiment from our observational study. Might not be possible, but we're going to try. So the propensity score is each subject's probability of being exposed to treatment, right? So my probability of getting denied, that's my propensity score. Steve, your probability of getting denied is your propensity score. Now, there's obviously a true score out there somewhere for both of us. We'll never know what it is, but we can estimate it. We can estimate it usually using logistic regression. So you just regress your treatment dummy, your 1 or 0 treatment dummy, denial, on all the covariates that you think matter to treatment assignment. And for each individual, you get a propensity score, an estimated probability of treatment assignment. And now, if my propensity score matches yours, now we have the same probability of getting exposed to treatment. Now we're a block in a randomized experiment. And so whatever difference in our outcomes, that is now attributable to treatment, having assumed everything that we discussed we assumed. Does that make sense? So basically, once you've estimated the propensity score, what you've done is you've reduced all your covariates to a single number, right? But that's the number that matters the most. It's the probability of being exposed to treatment, which is what allows us to recover that randomized experiment. And if, in fact, you're actually able to recover it, then you shouldn't even have to really worry about all the other covariates, right? If it's a big enough randomized experiment. So if you think about it, matching, if we could match exactly on propensity scores, we would have a perfect block randomized experiment, and we could, without bias, estimate treatment effects, right? Because we assumed everything else away. The best thing about matching on propensity score is that you can check if it worked before you proceed, right? So with other techniques, if you just use regression, say, and regress your outcome on treatment and then a bunch of covariates, you'll get an answer, right? You'll get an estimate, but you won't know if it's a causal estimate, and even worse, you don't even know if your model is right. Chances are it's not, but you don't even know if it's close enough to be useful. With this, and with other adjustment strategies, by the way, in observational studies, there's no good way to check if they work. As far as I know, though I did mention my bias, as far as I know, this is the only technique that allows you to check if it worked. So propensity scores, they will vary for each person, right? It's the probability of getting exposed to treatment. It's a continuous variable, so it necessarily will vary. It will probably be higher for those who got denied, right? Because they have more ones. Overlap is important. That's one of the assumptions that we've made earlier. And it's an estimated quantity, right? Whenever I actually get the true propensity scores, it's actually okay, because there are some chance imbalances that we see just because we sampled, and now this propensity score, because it's an estimated quantity, will actually balance those out. And importantly, and this is something that Jason just mentioned, so we might be 2 officers with the same propensity score, and we got there vastly differently. But that's not what we actually worry about. We worry about the joint distribution of all covariance, right? We don't worry specifically about the difference in our gender or the difference in our age or whatever. We worry about the joint distribution, and that's kind of, that's the answer to that critique, is that the 2 individuals are the same on the only variable that matters, which is probability of selection to treatment. Everything else kind of falls apart. That said, If you know for a fact that, say, gender matters to your decision to leave the Navy or not, which it does, what you can do is you can group people by propensity score and gender, right? Or you can say, or you can group them within a caliper and say, you know, I want them to match exactly on gender and on propensity score and be within 5 years of each other's age or something like that. You're not just limited to matching on this. If you are interested in balancing another variable as closely as you can do that. So there's a lot of buzz sort of surrounding propensity scores, and very infrequently do people talk about their shortcomings. So I figured I'd at least mention them here. One, again, they only adjust for the observed covariates, right? So whatever went into the propensity score, you might expect to balance that, and you might expect to balance variables that correlate with those variables as well. But it's not a magic bullet, right? If there's severe bias in your observational study and something you really left out, this probably won't cure you of that. As any statistical technique that's sort of regression-based, they work better in large samples, right? Particularly because you're usually using logistic regression to estimate propensity scores. Logistic regression in and of itself demands pretty high sample sizes. Demands a lot of successes and a lot of failures for every covariate that goes in it. And you really don't want to overfit your propensity score, because if you do, you'll get no overlap on the distributions between the two. But you can use different techniques, small sample techniques like fitting penalized regressions, et cetera, to estimate the propensity score. This is a pretty important point here. So the propensity score, you just put everything in the kitchen sink in the model, and you have your score. It doesn't treat variables any differently if they matter to treatment or if they matter to outcome. It sort of weighs everything the same, right? And in fact, variables that are important to your outcome are probably much more important to balance than variables that don't matter to the outcome. And then finally, misspecification. It's very difficult to diagnose. How do you know if you got that model right? You can assess model fit as you do with any other statistical model, but that's about it. That doesn't actually tell you you got it right. Now, I would argue that balance assessments, which I'll talk about in a second, help you get at this a little bit. But ultimately, as with any statistical model, there's no way to actually check if this is right. But again, usually, particularly if you're in the medical field, or you know, if in the military, for instance, as well, if you know how things work, that should inform your model, and then presumably you haven't misspecified it so badly that it's useless. So for our Navy officers, going back to that example, these are the box plots for the propensity scores. And so what we see here is, you know, the denied officers were more likely to be denied. That's not entirely surprising. There's actually a decent amount of overlap here. There's a bunch of officers down here who got approved, who it looks like never really had the chance to be denied. They were just superstars. Maybe they were really needed in the communities where they applied to, and they had no chance of getting denied. And then, so what do? What's a good, like these officers have decent matches on the other side, right? And these officers might not. And then that becomes your, you know, that's an art more so than a science. That becomes your decision as a researcher. What do you do with those folks? And that takes us to, oh, well, not quite. I'll get to it in a little bit, but there are different matching algorithms, right? You can figure out how to match people. If you're doing exact pair matching, you might think that there's not a good match for those people, and maybe the numbers don't even allow it anyway, and then these are good people to throw out, but just keep in mind, you just changed the quantity that you're estimating. If you throw out these folks, then you're now estimating the effect of treatment on the treated. You're no longer estimating an average treatment effect because you took out this. There are also matching strategies that will allow you, and I'll discuss them in a little bit, that will allow you to match people like this, right? And usually I think those are preferred because nobody wants to actually lose data unnecessarily. If these are valid data points, it's best to keep them in. So I mentioned earlier that one of the shortcomings of the propensity score was that it treats all variables the same. And in fact, all variables are not created equal, right? Balancing variables that matter to the outcome, that matter to your decision to stay or to go, it's much more important than balancing your session source or something like that. That arguably doesn't affect anything. And so in 2008, there was a paper that came out that said, well, let's take care of that. Let's take care of potentially balancing the most important variables, more so than the rest. And one way to do that is using a prognostic score. And that's a very controversial measure. The way that it works is it's very much like the propensity score, okay? But instead of regressing treatment assignment on a bunch of covariates, what you do is you take all your control subjects, okay, so all the officers who got approved, you take their outcome, some of them left, some of them stayed, and you regress that on covariates. So now you've built a model of staying and leaving only for those officers who got approved, okay? And you can use that model to predict for the officers that got denied. So you're kind of predicting their counterfactual. You're saying, I built a model out of approved officers about their stay-leave decisions. I will now predict if my denied officers had been approved, what would they have done? The problem with this whole thing, though, is that you're using outcome in the ways that you match people up. So you're using outcome already before you ever get to estimating treatment effects. And so I haven't seen a lot of usage of this technique. I think it's pretty controversial and people argue with it a lot. The information about outcome arguably should not be incorporated this early in the process, right? When you're just modeling early on. You're trying to learn about the difference in outcome, and now it's kind of a never-ending loop. So this exists. You can read it for yourself and decide how you feel about it. But I've been yelled at for doing this, and I think fairly so. What do you do once you've estimated a propensity score, prognostic score? They're all just ways to reduce your multidimensional X space to one single number, to one variable, right? What do you do once you have that number? Well, I've been mentioning matching and stratification. Stratification is a concept that was discussed for observational studies by Cochrane in his 1968 paper that is now quoted in so many observational studies. And in that paper, he mentions that if you have a disturbing variable, which is what he calls a covariate, right, that matters. If you stratify on that variable into just 5 categories, you might get rid of as much as 90% of the bias that's due to that variable, okay? So if you can just subclassify into 5 strata, you might get rid of nearly all the bias having to do with that variable. Well, now we have something like the propensity score, right, that has summarized our covariate in a very important way, the way that matters most. If we subclassify on that, if we just break that into quintiles and put people in those strata, if we believe that the propensity score is a balancing score for our study, we'll get rid of 90% of the bias. So it's a pretty magical finding. In practice, we can do even better than that. We can match people up. We can match them on covariates, right? Again, I mentioned earlier, we can match exactly on gender or on age or on something. Or we can match on propensity score. Or we can match on a combination of propensity and prognostic score, combine them into a Mahalanobis distance or something along those lines. And you can match within calipers. So you can say, I want people to always be this close on the propensity score or that close on the propensity score. So there are a lot of opportunities to do this, and this has really advanced with computing, not surprisingly, right? Because matching algorithms is something that plays into it. How do you match? Out of all our population, how do you pick suitable treated and control subjects to match? And how do you match them? Do you put them in pairs? Do you put them as a 1-to-2 matches or a 2-to-1, et cetera, et cetera? So first, they started out with greedy algorithms. So in a greedy algorithm, what you do is you order, let's say, treated subjects in a random order, and then for each one you just pick the closest control, out of the randomly chosen controls, right? And that approach works fine in large studies. In a smaller study, you could use something that's called optimal matching, and in fact, there's a concept called optimal full matching that will match everybody up. So in other words, when we look at this, a greedy matching will probably kick these people out. In fact, greedy matching might kick some of these people out because once you have matches for those, maybe you don't need the extras. So that's not great. And it might not optimize how close your matches are. In an optimal full match, you will use all of your approved and all of your denied officers. It'll match a bunch of these guys probably just to one person over here. And it'll match, you know, these, a bunch of those guys to each of those. And so basically you end up with some pair matches probably in the middle, but the rest of them will be 1 to k or k to 1 matches. But what optimal full matching does is it allows you to not throw anybody out of your data, which is really nice. Of course, every now and then you might get a configuration that, you know, is a 1 to 20 match or something, and you really might want to consider taking that people out of your sample and seeing at least if that changes your estimate or if it does anything. But usually, again, we try to keep everybody in. So usually you match. There are plenty of algorithms available to do that. In R, it's very easy. At this point, just press a button. It's all done for you. You can match on Euclidean distance on the propensity score. You can match on Mahalanobis distance. You can match on propensity score and other covariates. It's really your choice. But after you've matched, so you now have you know, a population, you've tried to recover your block randomized experiment, you've now created these blocks, right? So the next question is, did matching work? Did you ever recover your randomized experiment from your observational data? And that's what I like about matching or stratification. It allows you to check. How do you know if it worked? You know if it worked if your covariates are balanced now, right? If in the matched data set or stratified data set, if your variables are balanced. Well, how do you measure balance? And that's a very difficult question. And should you measure balance at all? So I would argue that you should, because you want to check if your technique worked. You can see if you have balance on observed covariates, and you may have balanced some unobserved covariates that are correlated to the ones that you measured and observed. And I think that that's very nice. And in fact, if you've stratified or matched and you're still not at the point of covariate balance, that's really useful to know. You should not be drawing causal inference from that data set. Maybe your propensity score model is misspecified. That's something you could worry about. Maybe your matching structure is incorrect. But you can go back and sort of keep working at it until you get to covariate balance. In all other techniques, you can't really check if they worked or not. All of that said, there's some pretty mean literature out there that says that you shouldn't test balance at all. And these are very prominent statisticians saying these things. So it's very much an unresolved issue. The problem is, in my opinion, is that many people measure balance incorrectly. So what they'll do is, once you have your blocks, your pairs, or your strata, they'll just do a t-test, right? They'll do a t-test to compare, hey, does the average age here now match average age over there? That's wrong for a whole bunch of reasons. One, you're doing a t-test, right, which compares means. And we're talking about balancing covariate distributions, joint distributions, by the way. So that's wrong to begin with. But they also get criticized in this literature because the power of the t-test goes down as your sample size goes down. And so, according to their argument, the researcher then becomes incentivized to just throw away data. So throwing away these guys all of a sudden now makes sense because I'll have a much more balanced, my covariate balance will improve just because the power of the t-test will go down. Now, my answer to that is, you know, we all have our integrity as researchers, and we shouldn't be throwing away data, and that's true regardless of whether or not you're doing a balance assessment. Another, and I think this is a valid point that the critics of balance testing make, is that a t-test is a quantity, a t-test is a test where you learn about your sample and you apply that knowledge to the population, right? And in fact, what we're interested in is the balance in our sample. Of our officers, we had about 1,100 officers in our sample. I just want to see, do I have balance on covariates among those 1,100 officers? I don't mean to be drawing inference to all the other officers in the Navy. That's not my goal. And so that makes the t-test yet another incorrect technique to do this. But there are permutation tests. There's randomization inference. You don't have to use parametric hypothesis tests that imply that there's a population you're interested in. That's how most people do it, and so they get criticized for it, but that doesn't invalidate the concept of balance testing. So with the help of randomization inference, we can actually perform balance tests, and we can see, did matching work? Does stratification on propensity score work? And if it did, we can move on to estimating treatment effects, because we can confidently say, we have now recovered a randomized experiment from our data. So what would you do? So if you have stratified or you've matched on the propensity score, you now have your blocks or pairs or whatever your matching configuration. You've done a balance test, and it looks like you've balanced your observed covariates. What's the next step? The next step is inference. Inference like you would do it in a randomized experiment. You could do randomization inference if you're comfortable no longer including covariates, if you think they're balanced enough. You could do a Fisher test or any of the non-parametric or parametric tests that we're used to doing, like ANOVA, regression, etc. You just include that dummy for which block the person belongs to in your regression equation or in your ANOVA. And then there are non-parametric adjustments, of course, available as well. Another thing, actually, I just realized I forgot to mention here on balance assessments is one of the critiques of balance testing is that perhaps you should maximize balance without limits. So in a balance test, once you achieve certain non-significant results, you're kind of happy, and you stop trying to make your matching or stratification better. There's a philosophy out there that balance should be maximized without limits, because that's what you get in a randomized experiment. Again, if you try to do that, you might be enticed to just throw away data or decrease the power of the test somehow. So I don't necessarily agree with that assessment. So once you've estimated your treatment effect, remember, because this is an observational study, we still have one more big problem, I would argue, to take care of. And that's, what if we miss something, right? Because if it's an observational study, what if there's a gene that causes you to smoke and also to get lung cancer? What if there's a lurking variable out there? What if some unmeasured concept causes the officer to get denied and also to leave the Navy, right? We need to test sensitivity of our results to leaving out a variable like that. And what it usually comes down to is, it's actually a pretty painful process, frankly, and most people don't do it, but it's very important. And what it comes down to is estimating a parameter gamma, and you can set it to various numbers. And what it does is it allows you to, I don't want to get into it too much here because it's a topic in and of itself for an 1.5-hour long tutorial, but you basically say, what if my exposed subjects had a much higher probability of getting treatment than my non-exposed subjects? What if denied officers were that much more likely to get denied because of some unobserved variable than get approved? So you try different values of that parameter, and you basically end up with a statement of, my missing variable would have to be this big in order to upset my conclusions. And then you check in your data and you see, does a variable like that already exist in my data? Is something like that plausible? And so in the case of smoking and lung cancer, I think they found something like a missing variable would have to have an effect 9 times that of smoking in order to upset the conclusions. They had now had so much observational data, and their story was so powerful that it's still possible they missed something, but that missing variable would have to be so enormous, and its effect on getting lung cancer would have to be so huge that it's highly unlikely that something like that exists. And so that's the story that one might hope for if you have observational study results. That yes, in theory it's possible to upset my conclusion, but my missing variable would have to be of this magnitude. It would have to be this enormous. And if it's not, then you actually have something to worry about, right? If something small could upset your conclusions, then at least we know that, right? Again, something we can measure. So any more questions on matching, stratification, propensity scores, and those kinds of techniques? Great, must have done a great job explaining it. So the next class of estimators that I want to touch briefly, because I don't find them especially good, but people use them because they're simple, are difference and difference estimators. And basically all it does is it compares the average change in outcome. This assumes longitudinal data. And so you observe a bunch of subjects before the intervention and then after, and you compare the difference between treated and control group after the intervention to the difference they had before. So it's pretty simple. It uses panel data. It has all the standard assumptions that you'd make in a regression, because that's basically what you're doing. And then it adds one more assumption, which is the parallel trends assumption. So in absence of treatment, the difference between treatment and control group is constant over time. And I found a picture of it, so I stole it. But the source is here, so it's not really stealing, right, if I'm quoting it. But basically, the assumption is just that if you had some kind of a difference between treated and control group prior to receiving the treatment, that difference has stayed, right? And then the rest of it was caused by treatment and not anything else. It's nothing changed, say, in the control group that made it go up abnormally. So it's a pretty standard assumption. You can't test for it exactly, but there are usually indications in the data. You can kind of check if you think it's true or not. So economists use this quite a bit, but it really, really relies on, on regression assumptions. Like matching of the propensity score ultimately is, it's non-parametric, right? And you can draw non-parametric inference from it. This, you very much have to rely on the correctness of your regression model if you're going to do this. And it's really easy to upset this. Another potential way to adjust is called instrumental variables. And this is very popular in economics. And the way it was introduced, actually, even before Fisher published his famous paper on experiments. But the idea there is that if you have a treatment and an outcome, and then a bunch of unobserved variables that affect them both, that you could use an instrument to unbias your results. So an instrument, and I think the example that people commonly use is, so there's smoking and lung cancer, and arguably things that make you more likely to do both or more likely to do one but not the other. You could use tobacco tax as an instrument. So it affects your likelihood to smoke. It's very much correlated with this, right? But it's not correlated with that. And so you can substitute and unbias your results that way. So in our case, well, let me go through maybe this first, actually. So the basic idea is you have your outcome, and you have your treatment here. And the problem is, again, if you have an observational studies, that this will be correlated with the error in a regression equation, right? Your treatment assignment is correlated with the error. And so we basically substitute for this something that's not correlated with the error, but is correlated with this, so it's kind of a good substitute. So in the regression equation, what you would do is use an instrument, z. First, you regress the x's on the z's, and then use x hats, the predicted x's from that equation, in place of x's in this equation. So again, in smoking, for instance, tobacco tax is very much correlated with a person's choice to smoke or not, but it's not correlated with the errors, right? There might be a gene that causes you to smoke and get lung cancer. That gene is unlikely related to the tobacco tax, right? So it's a good substitute. It's a good predictor here. And so in our case, I was trying to think of an instrument for a lateral transfers problem. In our case, maybe the recruiting goal. So the recruiting goal in the Navy, for that community, might tell you if that community is looking for people, if it's severely undermanned, or maybe it's overmanned, or if it's in high demand, or something along those lines. And so if you, it's certainly correlated with the officers getting denied or not. If that community is generally overmanned, they're probably not looking for more. Maybe somebody's more likely to get denied. But it's not correlated with an officer's loss. And so that's a good instrument here. The problem with instrumental variables is that it's very hard to come up with an instrument that everybody believes, right? And so some of those fistfights that I see in conferences have to do with, is this, whatever you use, is that a good instrument or not? And it's just about impossible to actually check that, right? So you don't know if it works. You can hope on a lot of theory, and that's not invalid, but it's much harder to make that argument with instrumental variables. So I'd like to conclude with this. I think this especially applies to observational studies, right? The correlation versus causation argument. This is really, so I don't know if this class has helped you. I don't know the causal effect of this, given that you self-selected to attend it. But thank you.